So this is an example of a paired t-test, and this problem is on the last page of today's handout, page 6. It says, does too much sleep impair intellectual performance? Researchers examined this commonly held belief by comparing the performance of subjects on the mornings following A, 2 normal nights sleep, and B, 2 nights of extended sleep. The order of these two treatments was determined randomly. In the morning, they were given a number of tests of ability to think quickly and clearly. One test was for vigilance, where the lower the score, the more vigilant the subject. Vigilance equals alertness. The following data were collected. Carry out an appropriate test to help answer the researcher's question. So it is asking us here to carry out a test. So that means this is a significance test problem. So for significance tests, we always use phantoms. And this just ensures that we're hitting everything that the AP exam is looking for. So let's start with P. That's where we define our parameter. And before we do that, let's think about this scenario a little bit. This is actually an experiment because it says the order of the treatments was determined randomly. In other words, we're randomly assigning treatments, so it's definitely an experiment. And this is actually a match pairs design. So we know that because each subject is getting both treatments, right? Both subjects are getting 2 normal nights sleep and 2 nights of extended sleep, and they're measuring the score on this exam after each of those treatments for each subject. So this is a match pairs design. And with a match pairs design, we get paired data, right? So what we notice here is this is actually just one sample. This is a one sample of 10 subjects, but we have paired data. And that's why we need a test like this, a paired t-test. And what we're actually going to be looking at is instead of looking at like the mean of, say, this first row of exam scores, instead what we're going to do is take the difference of each of these rows, and we're going to calculate the difference in exam score for each subject and calculate the mean of those differences. And the reason we do that is because each subject may start off at a different point. And sure enough, that's what we see here. If you look at this first row, there's quite a bit of variability in the exam score for the subjects who got, or for the normal sleep treatment, right? There's quite a bit of variability there. So because of that, different subjects are starting off at different places. So it's more meaningful to look at the difference in their score from normal sleep to extended sleep rather than looking at each subject's individual score. So that's why we're going to take the difference here, and the parameter that we're going to define is the mean difference in exam score. And this is a means problem. It's not a proportions problem because this is quantitative data. So we will use our mu symbol. So let mu. And since we're talking about a difference here, we use the subscript d. So let mu d equal the true mean difference in, and we'll call this the vigilance score. Vigilance test score. And just to be clear, we want to specify how we're actually calculating that difference, right? Are we doing the normal sleep score minus the extended sleep score, or the other way around? So what we're going to do is extended sleep score minus the normal sleep score. Of course, you could do this the other way around. That would just switch your alternative hypothesis, but let's just do it this way. Extended sleep score minus normal sleep score. And this is the true mean difference in those scores for all possible subjects let's just put for all possible subjects for this experiment. That's kind of our population. We're generalizing the results from these 10 subjects who went through this experiment to everyone who could possibly go through this experiment. That's the idea here. So that's our parameter. Now we need to move on to H. That's where we define our hypotheses. So we have our null and our alternative hypothesis. And I like to start out with the alternative hypothesis, defining that first. A lot of times that's easier. Here, we're looking for a test, right? We're doing a test to help answer the researcher's question. And the researcher's question is, does too much sleep impair intellectual performance? So, and it says here with this test, the lower the score, the more vigilant the subject, right? So if sleep impairs intellectual performance, we'd actually expect an increase in the score, because it says the lower the score, the more vigilant the subject. So the higher the score, the less vigilant the subject. So what we're really looking for here is that this difference here is greater than 0. So if the difference is greater than 0, that means the extended sleep score is greater than the normal sleep score, which means that the people getting, or after extended sleep, people are less vigilant than they are with normal sleep. So that's our alternative hypothesis. And then for the null hypothesis, we always use the same symbol that we used in the alternative hypothesis, and we use the equal sign, and we use the same number. So that's our null hypothesis. And basically what that is saying is that there's no difference in vigilance when participants get extended sleep or normal sleep. That difference is basically 0. That's what the null hypothesis is saying. The problem does not give us a significance level, so let's just use our standard alpha equals 0.05. Okay, so let's move on to A. That's where we check our conditions or state our assumptions. So the first condition is the random condition. So here they didn't talk about taking a random sample of people. And actually this is an experiment. So when we're looking at an experiment and we're doing a significance test, we just want to check that they're randomly assigning treatments. So that's how we satisfy the random condition for experiments. It did say in the problem, the order of these two treatments was determined randomly. So that condition is satisfied. So let's add that. The order of treatments was random. So that condition is satisfied. And then we can check the 10% condition. Now, the thing is here, they didn't actually take a sample like we just talked about for the random condition. So here, sampling with replacement and without replacement, that really doesn't apply here. And that's the case for experiments. So in truth, we don't really need to check the 10% condition here because we're not really concerned with sampling without replacement because they didn't talk about sampling. But it doesn't hurt just to put in a little line here about the 10% condition, just so that we're doing that consistently for all of our significance tests. So I'm just going to say we have 10 subjects here. Let's just put 10 subjects is less than 10% of all possible subjects. Okay. So then we have our normal condition. So remember, for the normal condition, there are 3 checks that we go through, and we go through them in order. The first check is the population distribution approximately normal? It didn't say anything about the shape of the population distribution in the problem, so we don't really know what that is. So we we can't use that check. So we go on to the next one, and the next one is the sample size greater than or equal to 30? Here, the sample size is only 10. We have 10 subjects. We have data from 10 subjects, so n is equal to 10, which is less than 30. And of course, that means we have to graph the sample data. So we need to graph the sample data. Okay, so I would recommend creating a box plot here, but the key thing is what data are we actually going to graph? So here we have these 2 rows of data. Which row should we use? And what we're going to do actually is calculate the difference for each subject and then graph those differences. And that's because we're not actually running the significance test on these individual scores. We're not running it on the normal sleep scores or the extended sleep scores. We're running the significance test on the difference between the scores. So that's why we want to calculate those differences. And we can use our calculator to help us with that. So I'm going to move to the calculator so that we can graph this data. So on the calculator, we want to go to Stat, Edit, so that we can enter in this data. So I'm going to put the normal sleep people, I'm going to put that in the first column. So we had 8, 9, 14, 4, 12, 11, 3, 26, 3, and 8. So that was the normal sleep scores. And then our extended sleep scores, those were 8, 9, 17, 2, 21, 16, 9, 38, 10, and 0. Okay, so then what we can do is actually calculate those differences in the third column. So in the third column, of course, you can manually subtract each of those pairs of number and manually calculate the differences. But we can use the calculator. Here, remember, we're doing the extended sleep score minus the normal sleep score. So here I want to do L2 minus L1. And to do that, just make sure you have L3 highlighted at the top. Make sure you have that L3 column selected. And then I could do second 2, which gives me L2, minus second 1, which gives me L1. So this is L2 minus L1, and enter. And it automatically populates those differences for me. So now I can create a box plot of those differences. So to do that, I can go to second y equals, and I'm going to turn plot 1 on. It is already on, so we're good there. And also we want to select the box plot for the type, and it's the box plot with outliers, so the one with the dots next to it. For XList, you want to make sure you have L3 selected, and to do that, next to XList, we can do second 3, and that will put an L3 there. I actually already had it there. And then we can go to zoom, so zoom 9, and that gives us the box plot. So let's see here. If we look at the box plot, oh, sorry about that. Let me go to trace, and that's going to give me the specific values. So I have -8 for the first, for the minimum, then 0, and then 4, and then 7, and then 12. So we're going from the minimum of -8 all the way up to 12. So we want to create an appropriate scale. So let's do that back on the problem. Okay. So we're going from -8, and I'll just go by 4. So -8, -4, 0, 4, 8, and 12. So -8, -4, 0, 4, 8, and 12. So my minimum was at -8. And by the way, here, these are the differences. So let's just put here score difference. And my first quartile was at 0. My median was at 4. My third quartile was at 7. And my maximum was at 12. So here's my box plot. And let me just make sure that's right. So on the calculator, yeah, we had 12 for the maximum, 7, 4, 0, and -8. Okay, so that looks right. Okay, so then we can clearly see here that we don't have any outliers. I didn't see any outliers on the calculator. Also, there is some left skewness here, but it's not that strong, so there isn't strong skewness here. So let's go ahead and put that. Sample data doesn't show strong skewness or outliers. So we can proceed. And basically what that means is, since the sample data doesn't show strong skewness or outliers, we can assume the population is approximately normal, which means that our sampling distribution would be approximately normal. And that allows us to do all these normal distribution, or t distribution in this case, calculations. So let's go ahead and move on to n. N is where we name the test. This is a one sample paired t-test for the mean difference, which we defined above as mu sub d. Then we can move on to t. That's where we calculate our test statistic. And let's start out with the general formula. So we are using the t test statistic here. And that's because this is a means problem and we don't know the population standard deviation. It did not give us sigma in the problem, so we do have to use the t test statistic. So the general formula is, and you can find this on your formula sheet, it's statistic minus parameter divided by standard error. So the statistic in this case, that's going to be the mean difference in this sample. And we can get that from the calculator. So let's go ahead and get that information from the calculator. So on the calculator, I'm going to go to stat, calc, one var stats. And here I want to make sure L3 is plugged in for list. So second 3, mine was already there, so we're okay, and go down to calculate and enter. So we can see here that the mean difference is 3.2, and then the standard deviation of the differences is 5.8652. So those are the two numbers we need. So let's go back to the problem. So I'll just write this down out to the side here. Our sample mean was 3.2. Write that again. 3.2, and our sample standard deviation was 5.8652. Also, we might as well calculate degrees of freedom. We're going to need that. So degrees of freedom, remember, that's just n minus 1, which is 10 minus 1, which is 9. Our sample size here was 10, right? 10 minus 1 is 9. So we have 9 degrees of freedom, and let's go ahead and fill in this formula. So our statistic is x bar. Our parameter, remember, when we conduct these calculations, we always assume that the null hypothesis is true, and our parameter is just the null value. So mu sub 0. And our standard error, we can get that formula from the formula sheet. It's just S In this case, we're looking at the differences. So let me actually add that subscript here. So I'm going to add that D subscript just to indicate that we're looking at the differences here over square root of n. So let's plug in those numbers. So our mean of the differences, that's 3.2, and then minus our null value. We can look back at our null hypothesis. That's assuming that the difference is 0. So we're going to plug in 0 here. And we have 5.8652 over the square root of n, which was 10. That's our sample size. So let's go ahead and put this in the calculator. So on the calculator, I'm going to have, on top, remember I had 3.2 minus 0. Well, that's just the same thing as 3.2 divided by, and then in the denominator I had 5.8652 over the square root of 10. Okay. So that is my t test statistic, 1.7253. So let's write that down. Back on the handout. Okay, so 1.7253, that's our test statistic. So I'm gonna go ahead and box that in. That's important information. And then let's go ahead and calculate our p-value. That's what O stands for, obtain p-value. And to do that, a lot of times it's easiest to make a sketch. So let's go ahead and sketch a t-distribution. And this is a t-distribution, and we calculate our degrees of freedom as 9. Remember that we're assuming that the null hypothesis is true, so that the true mean difference is just 0. And here, the sample mean that we got was 3.2. These are sample means on the x-axis, so that was 3.2. So we want to look for the p-value, we're looking for the probability of getting that kind of sample mean or something more extreme. So something more extreme would be greater than 3.2. And to help you with that sign, you can always look at the alternative hypothesis. The direction of the shading is always going to match the direction of the sign in the alternative hypothesis. So here we had a greater than sign. So then we're going to shade above 3.2. So that shaded area would represent our p-value. So we're looking for the p-value. We're looking for the probability that the sample mean is greater than or equal to 3.2, given that the null hypothesis is true, which is equal to the probability that the t-test statistic is greater than or equal to 1.7253. And we can calculate that with t-CDF in the calculator. So we're going to use t-CDF, and our lower t-score is 3.2. That's where our shading, our lower t-score is 1.7253. That's the t-score we calculated for this sample mean of 3.2. And we go all the way to 999. That represents infinity because the shaded area goes all the way out to the right, which extends to infinity. And then we need our degrees of freedom of 9. So let's go ahead and plug that into the calculator. Okay, so back on the calculator, I'm going to go to second vars and tcdf, which is number 6, and I'm going from 1.7253 to 999, and my degrees of freedom are 9. Then I can hit paste and enter. So there's my p-value, 0.0593. So let's go ahead and write that down. So I got 0.0593 for my p-value. Okay, so then I'm ready for m. That's where we make a decision. So we need to compare the p-value to the significance level. Remember, our significance level was 0.05. So p-value of 0.0593 is greater than alpha equals 0.05. And of course, when the p-value is greater than alpha, we fail to reject the null hypothesis. So we fail to reject the null hypothesis. So if we fail to reject the null hypothesis, that means we do not have convincing evidence for the alternative hypothesis. So that's going to be our conclusion. So there is not convincing evidence. And then I'm going to state my alternative hypothesis in context. So here, that the true mean difference, and then let's just go back and remind ourselves what the alternative hypothesis was. That was that true mean difference was greater than 0, and that was the true mean difference in vigilance test score. So that the true mean difference in vigilance test score, and we define that to be the extended sleep score. So I'll just put extended score minus normal score for all possible subjects is greater than 0. Okay, and then we could put that further into the context of the problem, right? Let's really try to answer the researcher's question. So here they're asking, does too much sleep impair intellectual performance? Well, what we found is that there's actually not a statistically significant difference between those two test results, extended sleep versus normal sleep. So here we actually don't have convincing evidence to conclude that sleep impairs intellectual performance. So I'll just put that in context further. And this part is kind of optional. Actually, what we wrote here is probably fine for a conclusion, but I just want to make sure we really understand what's going on in this problem. So we do not have convincing evidence that, and then let me just remind ourselves of that. Too much sleep impairs intellectual performance. So we do not have convincing evidence that too much sleep impairs intellectual performance. Okay. And then one last thing I want to do is show you how to check your p-value and test statistic using the calculator. So let's go back to the calculator very quick. So on the calculator, I can go to Stat and Tests. And this is actually a t-test. So I'm going to select t-test. There is an option for 2 sample t-tests. Here, just keep in mind, we had 1 sample. We just had 10 subjects. We didn't have 2 sets of 10 subjects. So here, this is in fact a one sample t-test, even though we had those 2 rows of data. So that's why we do use t-test here and not 2 sample t-test. So we're choosing t-test. And here, you could actually, since we have the data in the calculator, I could just use data. You could also use stats, but let's use data and let's make sure we have our null value was 0, so that's fine. We can leave that alone. And for list, we have that data in L3, so I'm going to use second 3 next to list to put it in L3. And our alternative hypothesis was that that mean difference is greater than 0. So we need to use that greater than sign to match our alternative hypothesis. And then I can hit calculate. And sure enough, the test statistic and the p-value that the calculator gave me, that matches what I calculated. So it looks like our answer is correct, and we're done.